Hess's law says that if we start with a particular set of reactants and then we end with a particular set of products, the overall change in enthalpy in going from those reactants to products will always be the same, no matter how many steps or what steps we took to get from those reactants to products. So basically this means that when we add two reactions, the change in enthalpy of the overall new reaction will just be the sum of the change in enthalpies for the two reactions that we added. So we have these two reactions here with a change in enthalpy of 180 kilojoules and then negative 112 kilojoules. And then when we add these two reactions to obtain this third reaction, the change in enthalpy of this third reaction will be the sum of these two enthalpies. So it will be 68 kilojoules. So this also says that if we start with N2 and O2, and we end up with 2NO2, no matter what steps or how many steps we take to get there, the change in enthalpy will always be 68 for the overall process. So with Hess's law, they'll often give you a set of, a couple of reactions, and then they'll give you a new reaction, and they'll ask you what is the change in enthalpy for this new reaction. So you have to find a way to manipulate the reactions that you're given in order to make them add up to that unknown reaction. Because we know if we add up those reactions to obtain the unknown reaction, all you have to do to find the change in enthalpy for that reaction is add up the individual change in enthalpies. So there are a couple of ways you can manipulate a reaction. The first is if you flip the reaction, then you have to flip the sign of the change in enthalpy as well. So if we just reverse this reaction, then the delta H becomes negative 180 kilojoules. And also we can multiply a reaction by an integer. So if we take this reaction and multiply all the coefficients by 2, then the delta H is also multiplied by 2. So something we're going to be using a lot in thermochemistry is the standard state. And the standard state is a reference state. You can think of it as similar to STP for a gas. STP is 0 degrees Celsius and 1 atm. Well, the standard state for thermodynamics is a little bit different from that. So the standard state is defined differently depending on if the substance is a compound or a pure element. So for a compound, all the standard state means is that if it's a gas, then it's going to be at 1 atm, and if it's a substance in a solution, it's going to be at 1 molarity. Now, so for example, the standard state of H2O liquid, it's just H2O liquid. The standard state doesn't really mean anything for that. If we have H2O gas, the standard state will be H2O gas at 1 atm. Now, for an element, it's a little bit different. So the standard state of an element is the form that it exists in at 1 atm and 25 degrees Celsius. So basically, standard state for an element means it's the form that the element naturally exists in. So for example, oxygen, the standard state of oxygen is going to be O2 gas. It's going to be in the diatomic form. Other examples, sodium is going to be just plain sodium solid. Mercury is going to be liquid mercury. Now, note that the standard state does not mean that it's always at 25 degrees Celsius. This is just a way to define the natural state of an element. So we can have a substance at standard state at other temperatures than just 25 degrees Celsius. Now this is different from STP for a gas, where STP always means 0 degrees Celsius and 1 atm. Standard state is more about the phase that the substance is in, gas, liquid, or solid, more than a specific temperature. However, for a compound, standard state does mean 1 atm for a gas and 1 molarity for an aqueous substance. So now we're going to look at the standard enthalpy of formation, delta HF, with this degree symbol. And when we see this degree symbol on a thermodynamic function, that means that all the substances in the reaction are at their standard states. So the enthalpy of formation is the change in enthalpy that occurs when 1 mole of the compound is formed from its elements when all substances are in their standard states. So for NO2 gas, this reaction is NO2 being formed from its elements, nitrogen and oxygen. And we know the standard states of nitrogen and oxygen are their diatomic gas forms. And so, remember, in enthalpy of formation, we need to form 1 mole of the compound. So that's why we have the 1/2 coefficient on nitrogen instead of putting a 2 on this guy. So the change in enthalpy of this reaction corresponds to the standard enthalpy of formation of NO2 gas. And you can see another example here with CH3OH liquid. It's being formed from carbon, hydrogen, and oxygen, where hydrogen and oxygen are the diatomic gas forms, and the standard state of carbon is solid graphite. So again, make sure you have the only one coefficient on the product, which is what you're trying to find the enthalpy of formation for. And so the delta H for this reaction is the formation enthalpy of CH3OH liquid. So we can use these enthalpies of formation to calculate the enthalpy change for any random reaction. So what we do is we take the sum of the enthalpy of formation of each product times its coefficient, then subtract the sum of the enthalpy of formation times the coefficient for each reactant. And remember that the enthalpy of formation for an element in its standard state is 0. Now, because an element in its standard state is already in its standard state, there's no reaction that corresponds to the enthalpy of formation. So, as an example, if we have this reaction, if we want to use the enthalpies of formation to calculate delta H, first we have the products, so 4 times the formation enthalpy of NO2 plus 6 times that of H2O liquid, then minus the reactants, 4 times enthalpy of formation NH3 plus 7 times that of O2, which we know is 0, since O2 gas is already an element in its standard state.